Good morning from California, and welcome to Race Industry Now, the weekly webinar series from ePowerTrade, presented to you by ARP, Performance Plus Global Logistics, PEAK, ShopMonkey, and Fifth Third Bank Motorsport. This is episode 329, and we're going to be talking CFD with EngSim. Good morning, I'm Francis Savignan, the founder and CEO of ePowerTrade, the global platform for the performance and racing industry. This morning with me are Judy Kinn, the co-founder of ePowerTrade, and our three-time NASCAR crew chief champion and host, Mr. Jeff Hammond. Judy?
Thank you, Francis, and thank you everybody for joining us today. I'm still thrilled to see all our new sponsors for this year that are supporting this program. Just deeply rooted hardcore racing categories, brands in here. And I just want to remind people that this is a platform where we've got thousands and thousands of buyers registered for access, just like walking up and down the aisles of trade shows, finding new products and services. I mean, look at today's webinar. It's just, there's so many companies in here and it's just a great resource. So make sure you use the platform. So, Jeff?
Well, good morning, folks. And I also want to say it's the second webinar I've done so far this year of 2023. And I am very excited about our great sponsors that have come on and aligned with us for this season coming up. So I can't say enough about our guest today, Dan Agnew. He came on during the industry week, put on an awesome display of what his company can do. And I look forward to see what he's got for us today. It should be exciting. And I'm also very excited about all the folks that are tuned in. And don't forget, ask questions. That's what this is all about. You want the answers? Hopefully he'll be able to give them to you. If not, we'll tell you how to find him so you can get the answers.
And I think Dan is on, so we're going to let you take over. We'll see you guys in 45 minutes.
All right. Thank you. Good morning, Dan. How are you?
Morning, Jeff. Good to see you again.
Yeah, it's good to see you, sir. And I hope that today's webinar is as equal to what it was last year during the industry week, because I found it very compelling. And again, I feel like, that since then, I know we had a couple times to reflect upon it. So what can we expect today? Earlier, like I said, when you came on last year, you kind of shotgun all the stuff that you can do. Your company is capable of doing multiple things. But today, I think you're going to kind of hone in and really kind of fine tune a couple of the items.
Yeah, well, today we're going to take a deeper dive into just one of the technical domains that we do a lot of work in, and that's computational fluid dynamics. Should I go ahead and share my screen and get started on it?
Yes, sir. You go right ahead, because as we talked about, we want to make sure we get questions answered today and have time to do that. So,
okay,
have at it.
Let me share here, and then there we go. Now we got it, I think. All right. I'm hoping you guys can see this screen. It's the title slide here.
Looks good.
Got that, Jeff? Good. Okay, great. Okay, what we're going to talk about today is more of a focus on the CFD of modeling of performance engines. Got a couple of slides, or 3 slides, basically just kind of giving you a little bit of background real quick on our company and what we do, why we do it, and some of the tools. And then I'll get into some the vast majority of today's talk is going to be talking about some of these case studies and some examples. And one of them I'm going to spend quite a bit of time on. So.
Dan, let me interrupt you here real quick before we get going. It sounds to me like we're having a little bit of audio challenge right now. You're a little bit garbled. Is there anything we can do on your end so we can help you out a little bit?
I guess I'll try and stay pointed at the computer. Thought we had that under control, but is that better?
That's awesome right there. That's awesome.
I'll try not to move. Okay. Well, EngSim's been around since 2003 doing this kind of work. I've actually been in the business for probably twice that long at OEs and tier ones and consulting companies. I've been at EngSim for, this is my 11th year, so quite a while there too. The industries we work in is obviously the OEM automotive has a lot of need for this, tier ones, industrial off-road, consumer, and then also the performance industry. That's what I'm here today to talk about. And we're a small company. There's only a few of us in here, but for many of our clients, they're also small companies that may not have their own engineering department, and that's where we kind of come in and fill that gap, fill that need to give them the engineering analysis tools and testing support that they might need. And then some of our work is also with the big OEs and tier ones too. But for those companies, they might already have a lot of these capabilities. So we kind of fill in there and fill some gaps where they may not have enough resources to do a particular job. So we may just step in and help them in some occasions where they just need a little bit of extra help. Some of the domains that we work in, I mean, any one of these domains is a whole day's presentation on itself. But I'm going to focus more on the CFD, which is all the way over there to the right. But we also do a lot of work in engines as a whole, vehicles, electrification of any kind of vehicle, not just cars, but any kind of vehicle. Valve trains, that's something that I spend quite a bit of time in, is valve trains, and then also a lot of thermal analysis. That's becoming pretty needy right now. If you watch all the newspapers with all the issues they're having in the electric car business, there's a lot of thermal issues there, and these kinds of tools can help a lot of that. You might ask yourself, well, why do we do this? Why do we care? I'm not pitching this as a replacement for good design and good testing, but actually a supplement for it. The testing is very important, and good design is very important. But this kind of analysis really makes that work much more targeted and efficient, and can improve the understanding. A lot of times the testing is, you get good overall numbers, but you don't really understand why something happened. And this kind of analysis really likes to take a deeper dive into understanding those whys. And you can take those thousands of crazy ideas and just filter them down into just a few reasonable ones, and then to go on with very targeted physical testing. For example, we're looking at a cam development program now with a race team, and they're trying to come up with a new cam, and they probably got 100 cams that they want to look at. Well, that's not very practical. They're going to blow up some dyno engines, burn a lot of fuel. We don't do any of that with this kind of analysis. So we can filter all those ideas down to just a few reasonable ones with this kind of analysis. And there's a lot of tools out there, and there's a lot of resources to help you pick from. So I'm hoping I can just kind of stimulate a little bit of that thought process to go either look at some of these tools for yourself, or look at trying to get some help on your projects from companies like us, maybe. The 3D software that I'm going to spend most of the time today talking about is it's Converge CFD. That's the brand, and it's not a software that we sell. That's a software that we use. We actually have to pay them a lot of money to use this software. We're not a reseller, we're a user. We like this software because it's very well tailored to engines. A lot of softwares out there, some of them are really good at doing external body kind of flow work. Some of them are really good at doing internal kind of flow work. And Converge not only does it'll do it all, but it's really tailored to engine work, and especially when you have moving pistons and moving valves doing transient flow. And then if you want to or need to incorporate a lot of the other physics platforms like acoustics and thermal, mechanical, chemistry is real big. If you're looking at doing combustion analysis, then you need a really good chemistry module in there. And electrical, you can, if you're going to put a spark plug in there and light it, then you need some electrical physics going on there too. Like I said, this software is really well suited to doing moving pistons and moving valves while you're doing the flow. You can do turbochargers or water pumps with like rotating impellers, that kind of work. It's really good at exhaust after treatment. That's not so much a topic for this kind of an audience looking at emissions. and that kind of chemistry, but it's certainly very good at that. And it's got really good pre and post processing for bringing in your CAD data, setting the model up and running it, and then looking at all the results. You get so much results out of this. You could spend weeks and weeks just looking at the results of one run. And it's got some really good modules that help you take care of that. And then it's really good at distributed computing. You could run this on a laptop, but it's a little cumbersome. We do most of our work in the cloud, where we move the model up to the cloud, run it, and then bring it back down to us locally to do the post processing. And it couples really well to other people's software too, like 1D codes, like softwares like GT Suite or GT Power, if you're familiar with that kind of stuff. Just a quick comparison, at the risk of maybe oversimplifying this, I wanted to go through this for a moment here. But to compare this kind of CFD work with like a traditional flow bench, if you're doing that kind of work, the resources you need, obviously on the flow bench, you need a flow bench. You need fixtures, you need machining, equipment, testing accessories, you need computer software or a spreadsheet if you're doing any kind of data management with it. For the CFD, you need a computer workstation, you need software, and you need a license. Personnel with the flow bench, you need an experienced technician and a machinist to help you build your models. Similarly, with CFD, you need an experienced CAD or a CAE engineer. For a test model on a flow bench, you need a flow box. You need something to test. You need the flow box or a head or manifold or whatever you're flowing. On CFD, you need a CAD model. You got to have some kind of a CAD model to be able to work with. And the output on the flow bench it's pretty general and overall, looking at flow capacity or some in-cylinder motion, swirl or tumble. With the CFD, you get a lot more. You get, not only do you get that flow capacity and those general overall mixture motion kind of numbers, if you're looking at in-cylinder stuff like we're going to look at today. You get very detailed and localized speed and direction. You get heat transfer. If you move into some of the advanced combustion with transient flow, then you can get burn rates. You can mix fuel, air, PCV, EGR. You can put anything you want in there. I got 4 case studies. The first 3 here, I'm just going to kind of touch on because these are all very different kinds of applications of the software. First one is a block and head coolant flow, and then we're looking at an enclosure, or which you could compare that to like an underhood airflow or London engine. And then I've got kind of an interesting example. It was a real simple overhead valve generator application, but you could certainly extend that to doing any kind of engine. And that's going to demonstrate some transient flow with moving pistons and moving valves and combustion. And then I'll spend the bulk of the rest of the presentation here talking about double overhead cam intake and exhaust port flow. And here I just modeled the scope of this project, and all I really had time to package up for this kind of a presentation is the steady flow with fixed valve lift.
Hey, Dan.
Yes, sir.
You know, we talked that we might want to just take, we're getting some questions coming in.
Yeah.
And I don't want to get too far ahead of, so like I say, before you get into another part of your presentation, I want to make sure we get these addressed now, and we'll do some more as we go on.
Sure, go ahead.
Peter wanted to know, please describe how you select the cross-sectional area of an individual runner and intake exhaust manifold, for an example, is one of the questions. I'm going to give you all of them, and you kind of answer them how you feel. He said, coincidentally, I just listened to an SAE presentation on Converge by Kelly. And
okay. Yeah.
Also, does your company have a lot of experience with fuel prep and its effect on combustion efficiency?
Okay, I did the first question. If I understand that right, someone was wondering how we pick port, cross-sectional area, and runner length. Was that it?
I guess, yeah. How do you pick which area you're going to work in?
Which one I'm going to work in? Well, it kind of depends on what the customer's looking for, what their objectives are for the project. This particular project, we're trying to get the best airflow we can and try and understand. Well, and I'm referring to this last project here that I was going to talk about. In this particular case, we're trying to get the best airflow efficiency we can with the valves that we've taken up in the cylinder head. And as far as runner length goes, I mean, that's usually dictated by the package and what your torque and power requirements are. And then I guess the next, I'm not sure that the second one was a question or just a statement about Kelly. Kelly's one of the principals at Converge, and and he travels the world talking about CFD and specifically CFD and engines. So that's good. It's interesting. He's an interesting guy. And the last question, you got to go back and let me know what that last question was.
Okay, 1 second. I can pull it right back up here. It says, does your company have a lot of experience with fuel prep and its effect on combustion efficiency?
Okay, we've done some of that where we have it's either DI or port flow or port injection, and we've done some of that with the transient work. Yeah, you have to address that. That is part of the project, really. It's a very integral part of the project, especially with DI. I mean, that's really key with the direct injection type of application. So I guess the short answer is yes. That's kind of built into any kind of transient advanced combustion kind of CFD project.
All right. Okay. Let's say, hang on a second, from Peter again. Each manifold may produce one single plane torque peak or two torque peaks. Hang on a second. That thing dropped off there real quick. Hang on. Or two torque peaks. Sir Harry Ricardo, 1931 patent said, set time average flow velocity in a single intake runner at 80 to 180 foot per second. It's a single plane. I found 212 foot per second works the best. Do you get into that detail?
We can, but with a steady flow CFD, no, not so much. That's more of a 1D, like a GT power kind of analysis where we're looking at runner geometry and port flow, valve sizing, that kind of stuff. And then we can take that and put it into a transient CFD run where we can even with a 1D. I mean, we can look at those flow speeds, those airflow speeds in a transient run in 1D code or in a 3D code. And I got a slide that might address that here in a couple of minutes.
Okay, sounds good. And
Okay.
thank y'all for your questions so far. Again,
Okay.
I want to make sure we keep you updated.
Okay, should we move on then?
Yes, sir. Move right on.
Okay. Okay, this first example is coolant flow. The purpose of this project was to look at the coolant flow distribution through a block and cylinder head, and then the only thing we had to play with here was a head gasket due to investment, that people didn't have the investment money to go and look at changing sand cores, but we could modify the head gasket. So we wanted to take that and look at. I'm not sure if this shows up because on me this option 3 the screens are covering it up. I don't know what that looks like on the rest of everybody's screens. But anyway, this picture on the left is the convective heat transfer coefficient, and that's an indication of how well you're going to be transferring heat to the casting, to the block and the head. And this is the baseline case. And you can see there's a pretty good distribution from the water inlet to the water outlet thermostat area. And so that's one thing, an indicator of whether we've improved anything. And the second picture kind of in the middle is pressure. You want to be able to manage the coolant pressure through there. And then we had a baseline here, and what I'm showing here are the percent of the average of the flow through the head gasket passages. And you can see there's a pretty wide, we go from all the way to 145% of the average down to 58.3%. And by the time we got to option 3, it was pretty well, so I can move this over here now. Didn't know I could move that. Okay, we got it pretty well distributed. I mean, we go from 102% or 97% down to 91. So we made some pretty good improvements just by playing with the areas of the gasket. So that's the kind of work you can do with coolant flow in a block. This next example, move this bar back over. This was a case where we're looking at the airflow through an enclosure. This happened to be a generator package, but you can imagine this could be an engine under a hood too. And the purpose of this was to evaluate and recommend changes to the airflow distribution and to optimize the air velocity, which they're concerned about noise. And they said if we could make the air velocity more uniform and make it go down, well, then that's going to make it quieter and maintain an acceptable temperature distribution. And you can see this. The picture on the left here shows what the velocity field is. You can see it's all over the place. So you got some real extreme velocities that go up and over it. You got some pretty quiet velocities. And then in one iteration, we were able to make that very uniform, playing with the front entrance on this enclosure. We have a very uniform velocity gradient in the front, and it's pretty uniform throughout there. So, and then that indicated that really leveled out the temperatures inside there. So that's just an example of some of the underhood kind of airflow applications we can apply this to. I'm going to play this video here. This is an example. This is the transient moving piston moving valve. Hopefully, if we've gotten the bandwidth going here, you can see this flame growth. This is just going to run while I'm talking about this here for a minute. But there's basically three different levels of in-cylinder transient analysis. One is the cold flow. You're only looking at the flow up until the point that the valve closes, and you can learn a lot about how the mixture motion is set up and the port flow efficiency. If you add in the compression stroke to just before the spark plug, that gives you a good indication about what the flow field is right there at the spark plug at the time of ignition. And then if you go for broke, you can add in the combustion and the flame growth here, which is what I'm showing in this example. This is a pretty extensive, complicated analysis. You can see how the flame just kind of develops, goes across, and then it just kind of wraps around itself as the piston goes down in the expansion. Okay. In the last case I was going to talk about today, this is one we're going to take a little bit deeper dive in here. The purpose of this project was to supplement flow bench testing with an early evaluation of a concept port to help try and direct the hardware development with both quantitative and qualitative data. And the process here is we used a 1D engine simulation. This is where we pulled in GT Suite to support setting up the CFD scenario, so to speak. And then we import the CAD to the CFD preprocessor to mesh it and to set up the valve list. And then we solve the CFD case and post-process it. This is a picture of the 1D engine simulation engine model that we used to answer some questions and ask some questions and answer them. If you see here in the middle, I'm going to show you some plots in a minute here to look at where we tapped and looked at what the port pressure to get the mass flow is. This is the cylinder and the port. I'm showing the exhaust, but the same thing goes on the intake too. And then where the valve lift is probed in this model. And this is going to help us answer a couple of questions. One is that what pressure or vacuum should I use for my CFD model for flow bench testing? And then where should I put my effort in the port flow optimization? Should I look at low lift, mid lift, or high lift? And then what's the effect of my changes on engine performance? So ultimately, this is what we want. This is what we want to answer. That's kind of the next step beyond the analysis that I'm going to show today. This is kind of a busy plot, so kind of try and bear with me here. I'll try and break this down a little bit, but this helps answer in my mind what pressure I should use in my CFD model or my flow bench testing for that matter. Historically, I mean, I've run flow benches for a long, long time, and 28 inches of water has always been the pressure drop we use across ports. But as I show here, this came from an engine simulation model. That number is not very realistic. This red dotted line here is the exhaust valve lift. The blue dotted line is the intake valve lift. This orange line that comes down is the cylinder pressure. And then this red dashed is exhaust. That's the exhaust port pressure. So you can see at 3 millimeters of lift, I have 900 inches of water delta P across that port. Compare that to the 28 inches of water that we run on flow benches. That's not a lot, big difference. Even at 6 millimeters, we're 301 inches of water. When that exhaust valve opens, when it first cracks open, you're sonic flow instantly. And that's a little hard without some pretty heavy duty equipment to simulate on a flow bench. On the intake side, we're a little bit closer, but we're still not there. At 3 millimeters, I see an 88 inches of water delta P, again, as opposed to 28 inches on a flow bench. At 6 millimeters, we're a little bit closer. We're 44 inches of water delta P. So that just kind of puts in perspective. I guess what I'm trying to say is you got to keep that in mind when you're doing your flow bench testing, that what you're looking at might not be very realistic in a real running engine. But to help answer the question about where in that valve lift curve should you be putting your effort, what I'm showing here is mass flow in the solid line. That's exhaust mass flow with the red solid. The red dots is the exhaust valve lift. The blue dots is the intake valve lift, and the blue solid line is intake mass flow. And you can see here that you have peak mass flow at kind of a mid to low exhaust port lift area. So that tells me that I should probably be putting most of my effort or concern on an exhaust port at the low to mid lifts and not worry so much about the high lift numbers. Whereas the opposite is kind of true on the intake, where you spend a lot of time at the mid lift in the peak areas of the mass flow curve. So I think that's where most people spend their time. It's kind of been intuitive, but it just kind of reinforces that. This happens to be at the peak torque engine speed case. All right, now we're gonna talk about the CFD model specifically. We start with a CAD model. You got to have a CAD model. You can't really do much without that. From that, we extract a solid air core of that model. And we bring that into the preprocessor to mesh. This is done with the Converge preprocessor. You can see that here we have this model set up at 3 millimeters of lift. You can see the spark plug here, this little green square in here is a side view of the spark plug gap. One thing that we did on the intake is we separated out this disc in the middle to look at mixture motion. We wanted to just come down a little bit from the top of the cylinder, and from this we're going to be able to look at swirl and tumble. And as similarly on the exhaust, I'm not concerned about mixture motion on the exhaust side, but the model is constructed much the same way, the mesh model here. So I take this and then I set this up for an intake, kind of a flow bench simulation. I have a big plenum on the intake, all these red panels, that's where the air comes in. It kind of simulates the room that the flow bench is in. And the light green around the bottom, that's like the plenum at the bottom of the flow bench. And we set this up for this study here at 70 degrees F and 28 inches of water vacuum. We have 3 cases. One of the intakes are at 3 millimeters, intakes at 6 millimeters. And then another case, just we are curious what it would look like if we put one valve at 3 and one valve at 6. On the exhaust, much the same. We put a big plenum on the port outlet. and then use the same plumb on the inlet, set that up again at 70 degrees F, and 28 inches of water across from one plumb to the other plumb. And here we looked at 3 millimeters of lift and 6 millimeters also.
All right, Dan, let's address some of these questions before we get much
Sure.
further along here. Jerry would like to know, or Jerry, Jerry, how do you handle cylinder variation of boundary conditions in a two-plane V8 combustion model? That's one question for you.
I guess I don't know if I understand the question. How do we address boundary conditions?
How do you handle cylinder variation of boundary conditions in a two-plane V8 combustion model?
A two-plane. I'm not sure if he's talking about a two-plane intake manifold. I guess I'm not sure exactly. Maybe if we can ask him maybe to clarify his question a little bit, and we can come back.
Okay, get back with us there, Jerry. And then Andrew wanted to know. Hang on a second here. I'm having a little trouble with my fingers today. Hang on here, Andrew. Every time I move this thing it's jumping 400 feet in one time. Do you only work with engine developers on an individual product basis, or do you have any NDA agreements with engine efficiency parts manufacturers? I am, let's see, what else did he say? I think he wants to supply CAD files under some imaging for valve manufacturers or intake manifold company potentially supply you with CAD files under an NDA whereby you could swap out components on your engine developer engines and let them know if there's an expected efficiency gain in whatever they are looking to optimize, if they would do that on a trial part swap. I think he just sent you a contract.
Yeah. I'd have to send that to my lawyers, but we do, most of our projects are under NDAs. This particular project that I'm showing you here is an internal self-funded project that we're looking at. But we do operate on NDAs. We do have some of our own like GT Suite engine models that are kind of generic that we can tailor to new projects. But we don't, I mean, we're not exclusive to anybody at this point. Not that we can't be, but that gets expensive when people want exclusivity. And we do kind of work collaboratively on some projects that can be disclosed. You know, if we're going to write a paper on it or use it for marketing, then we also have ways to operate that way. So I think I answered his question, but I'm not sure.
Well, like I say, we're still here. They can do a follow-up question if they'd like to. Richard wants to know, have you done any work simulating asymmetric cycles by early intake valve closing?
Yes, we look at all kinds of different type of cam timing arrangements that, you know, look at things like Atkinson, those kinds of cycles. We have a project like that going on right now with somebody. So we do look at a lot of those kinds of projects. And you have, with these kinds of models, you have that flexibility to do that kind of stuff very easily.
All right, Jerry's got one of these questions here that I'm going to read it and do the best I can with it, because if you run higher pressures, how do you, with relative independence of the choked flow G/S, again, I don't know what some of the stuff that works, but when you are choked, he's got it in parentheses, once choked, flow is constant regardless of pressure, right?
Yes. Yeah, when you choke, when that valve let's say when the exhaust valve first cracks open, more often than not, you're going to be choked right there, and yeah, that's flow limiting, and then it falls off from choke from there on out. So, and this CFD software addresses that just fine, and so does the GT Suite in a 1D. It's got the physics built into it to address those choke flows.
And Frederick would like to know, does Converge have the capability to compute compressible flow and predict the presence of shock waves?
Yes. It's all, everything is compressive in here. It's not incompressible flow. It's all compressive.
All right, that catches us up, and we still have some time here to proceed. And
okay. Looking at this quantitatively, the results, I'm going to move my little screen down here. The flow capacity, I mean, these, unless you got something to compare them to, they don't mean a whole lot, but we in this case, I'm only showing one case, so it doesn't really do you a lot of good. The discharge coefficient does me a little bit of good, because I look at these and say, okay, these aren't very good. These are pretty low numbers. This is based on the valve head, OD. To me, that's an important parameter, because the valve OD is what kind of takes up cylinder bore space. That's very, very valuable real estate. So you want to make the best use of that as you can. And in my database that I've been looking at for 40 years on CDs, these numbers are pretty low. And the other thing that's interesting here is what I have here is angular momentum flux around the x-axis, y-axis, and z-axis. Now that's basically swirl. You look at this, these axes I have down here at the bottom. The z is what I'm calling tumble, x is swirl, y is what I call twirl, which is a combination of swirl and tumble. And you can see, looking at these numbers, that like with a 4-valve cylinder head like this, it's going to have a propensity to want to make some tumble. And okay, yeah, these numbers were compared with the other axes around 10. I mean, for all intents and purposes, these are nothing. They're zero. Once you start looking at the z-axis and tumble, okay, you start getting some numbers there. So that's the kind of insight you can get if you set this model up to look at in-cylinder mixture motion. I'm going to have to zip through some of these slides just because I think we're kind of leave some more time for questions. But I could spend an hour just looking at this one slide here, and I see something new every time. But this is a section. This is at 3 millimeters of lift on the intake. I'm looking at a slice right through this middle of one of the valves, and you can see from an overall standpoint, we got pretty good flow development through the port. The entrance to the port, it's a little bit off center, but I'm not sure if I need to be concerned about that yet. I don't think so yet. But you can see what this isn't technically choked flow here, but you can see it's very restricted flow right there at the valve seat at 3 millimeters on the intake. And you can see there's going to be a lot of propensity to separate there. If I zoomed in even farther, you could see separation. But these are the kinds of pictures that in my career, I've had a lot of, I've worked with a lot of good flow bench technicians. And when I show these kinds of pictures to a flow bench technician, I mean, their eyes just light up, because, oh my God, I've never seen the air going through the port like that. You can stick your finger in it. You can stick all your little probes and tools, and you can poke around in there and see whether you affect, but you can't see the flow. Here I'm showing these flow bench techs that I've worked with, what the flow looks like, and it's very enlightening in that kind of situation, where that guy can then go back and do some much better development once he can see what the physical flow looks like. This is a section through the spark plug, again at 3 millimeters. So you can see you got some flow through the spark plug at 3 millimeters of lift. I'm not really sure how much I care about that, because a lot goes on, but after you close the valve and the piston comes up. So what the flow right now is through the spark plug, I'm not too concerned. But you can see it's just kind of a whole mix of motion. You have a little bit of rotation in here, which is good. it shows a propensity that to develop some swirl. And then here's some flat sections through some horizontal sections. These big ones are down a couple of sections below the valves, and then I move up this section. You can see I'm starting to cut through the valve, so you can see the two fields that the flow makes up below each valve. And to get up into the throat, you can see how the flow is very different on the short side versus the long side, which makes sense. And you can see all the flow separation on the back side of the stem and around the guide. Not a whole lot. I mean, you got to have a valve stem in there, so you're always going to have the flow is always going to be a little messed up behind the valve stem. But there's probably maybe some work you can do around the guide to help that. And then you get farther up the port, and it's pretty uniform, so that's a good thing. I'm gonna skip through the 6 millimeter here to save some time, because I want to show some of these others. This is a 3 and 6. This is a section through the 6 millimeter valve. But I want to make sure I show the exhaust, because I think that's I learned some lessons here about setting up these models. So this is the exhaust at 3 millimeters. This is a section through the valve. They're both at 3 millimeters. And when you zoom in, you can see there's some recirculations and some loss on the back side of the head of the valve. You can see a lot of separation. This big blue area on the short side. The flow looks like it just wants to come in here and detach and go to the roof. So that's a lesson we're learning here. And then on the long side of the port, it comes in and hits the stem and the guide and gets kind of messed up behind the guide too. And the other, I'm going to show, this is through the spark plug. So through the center of the spark plug, the way the port is designed, you're looking at kind of the end of the port. You can see where the flow is pretty well stuck to the roof, and then it just shoots up. I want to show this at 6 millimeters also, because it's even more exaggerated at 6 millimeters. Look at the way this flow just kind of takes off through the port. And kind of what this tells me is that the setup I have here is probably not as good as it should have been. I probably should have put a section of pipe out here to extend it, because this is not realistic. In the real life, the exhaust doesn't just dump into the room. It goes into a manifold or a header pipe or something. So we probably, to be more realistic, I probably should have put a section of pipe on here. That's very typical in doing flow bench testing, but this demonstrates why you would want to do that. And the next time through this CFD study, that's what I'm going to do. I'm going to make this plenum bigger, and I'm going to put a pipe on it. So that's one of the lessons we learned. The horizontal sections. So I think I want to save some time here. I mean, I pretty much talked through some of these observations already. That I think that this indicates that the flow capacity could be improved. The CDs kind of indicate that there's some help. The exhaust short side detaches, pushes to the roof. Modeling demonstrates the deficiency with the exhaust port outlet and plenum the way I modeled it. That needs to be improved next time. So where I see this is going, just as a kind of wrap up here and maybe have a few time for some more questions, I think you're going to see, I mean, this industry is just growing at leaps. It has been for decades, really. It's going to continue to see that, and it's going to get faster and faster. There's going to be a lot more development like combustion and emissions, exhaust after treatments. There's going to be a lot of combining a lot of these models together. Everything's just going to get faster and easier to use. And then I'll leave this up here while we're maybe answering some questions. Just as a reference, these are things I have on my shelf. This is a SAE paper that I did quite a while ago where I talked about all those discharge coefficients. If you're interested, you can pull this down from SAE. And then my favorite textbook, Gas Flow in the Internal Combustion Engine. And then my contact info. If you need to get a hold of me, you can either do it through ePartrade or write this down, or you can, find me on LinkedIn or anywhere. So, Jeff, was there any more questions or?
Yeah, we do. We've got some more questions as we get here toward the end of our webinar. And Andrew was trying to get some clarification. He thought maybe the main part of the question would be if you develop a repository of a CAD model that could trial with your clients that are not generally available. For example, if we have a part that we have shown to have varying efficiency increases depending upon the engine, would you have an interest of a CFD model modeling all the available engines out there in order to show expected gain per engine? But we would potentially provide your CAD model under an NDA for you to utilize your customer simulations, provided your customer has never obtained the CAD file. Is this a bit different than the exclusivity angle, which you took to answering the question on? However, I think I found my answer when you were given the question, so it was misunderstood. So the follow-up question: would your company have an interest in developing this kind of a deal?
Yeah, I mean, we'll talk to anybody about deal.
Okay.
We do that. I mean, no two projects are alike, both from a commercial standpoint and a technical standpoint. So we're open to any kind of variation on that.
And Frederick would like to know: does the analysis presume a discharge coefficient that is one computed at 28 inches, even though the pressure differences in the simulation makes it be significantly different than 28 inches? And he said, I'm referring to the unsteady simulation.
Yeah, well, I didn't calculate a CD with the unsteady simulation because it's gonna vary a little bit. I mean, theoretically, the CD is going to stay consistent, independent of pressure drop. The only time that would change, I think, is that if we went to say we could go to 900 inches of water somehow on a flow bench, the flow field across the port's probably going to look a lot different. But if the flow field stayed the same, then the CD should stay the same. And I don't calculate that on a transient basis. So I think that answers his question.
Well, like I say, you now give him a way to reach back out to you for further questioning. Yep. Peter, real quick, said, hey, the V12 Allison engine used during World War II in the P-39, P-40, and P-51 fighters had a hemispherical shape on the bottom in the cylinder face of the valve. Have you ever studied that?
Not that hemispherical. That was very hemispherical back in that day. I mean, yes, Chrysler did come out with what they called a Hemi. Their current, what they currently call a Hemi, and it's kind of like a hemispherical, and we've done some studies like that.
Right.
But we haven't done an engine like the Allison, but certainly can be done. I mean, there's no reason it can't be.
Okay, with what we did here today, Robert would like to know, for the example shown, how long did the simulation take to run? I think that's a really good question when you're doing something like this.
Yeah. If I move this up to the cloud, one of those steady flow runs probably runs in about 5 or 10 minutes. I mean, I measured in how many cups of coffee. I can hit the go key, go get a cup of coffee, have a few sips, and it's probably done. You spend a lot more time post-processing it and looking at the results and just because every time you look at a new plot, then I come up with another question and I want to look at it another way. So the actual CPU time is clock time with the number of processors that I run is probably 5 or 10 minutes.
All right, and a follow-up on that, Robert also wanted to know, at what level of cost could the end user expect to pay for an analysis?
Okay, what I showed today, assuming we get a good CAD model, because we can spend a ton of time fixing a CAD model and repairing the mesh model because it was not a great CAD model. But if we get a very nice, clean CAD model, this kind of analysis can be done in just a few days. And that, you know, a base cost on it would probably be, I mean, there's no two projects that are the same, but a base cost would probably be on the order of low 4 digits in dollars.
Okay, very good.
And then and then you got that baseline model that you can go on and on and on with. So the second time is going to be cheaper, and the third time is going to be cheaper. So.
All right. And Peter said, hey, you wanted to make sure we got this clarified. I wasn't talking about a Hemi head. The Allison valves had a round bottom instead of a flat surface.
Oh, the valves. Yeah. No, that is important. And it certainly can be studied. I mean, generally, the projects we've had, we're handed a valve model and said, here, use this valve model. And then, if we see an issue, then we'll go back and make a point that's something that our client should go back and look at. But that on the projects we've looked at, that wasn't an option for us. But he's right, that is important.
And Robert Gherkin wanted to know your combustion slide showed a secondary ignition area. Was that detonation? No. They were paying attention. Attention.
No, that's a really good question. No, that particular video was a slice through the center, and what he saw that it kind of came up out of nowhere was the flame front kind of splits in half, and then it comes back around the backside of the bore and folds back on top of itself. So it's one flame front, but it's really operating in 3D. It's not a new flame front. Good question. Very observant.
Yeah, and Robert Kirk said, thanks. It's very interesting. How many processors or CPUs are you running on a cluster?
Oh, geez. I think on this project I ran 32, if I remember right, something on that order. That's kind of why we run them up in the cloud, because we're basically renting CPUs, and we can rent as many as we want. If I want 64 or 128, and when I said 5 or 10 minutes, I'm referring to this steady flow run. To do a run like that combustion run, that could be a couple of days using 128 CPUs, something on that order. So that's an order of magnitude more complex and time intensive.
Well, Dan, as always, thank you. I mean, like I say, you're working in a I'm gonna call it the 3D world that has got endless opportunities and areas of where we can take things and we want to see what it looks like when we can't see it, and I think that's awesome. And I'm glad to see that our participants today were engaged. I do appreciate y'all being a part of it, and really excited about today.
If anybody needs to follow up, hopefully you got my contact, or go through RepartTrade and find me there, or LinkedIn, and be happy to talk.
Well, thank you very much, Dan. Brilliant presentation. We actually pushed EngSim back on the homepage of RepartTrade, and so if you want to connect with Dan, you can go on the platform, or I'm sure you were able to get his contact information. So thank you very much for being with us today. This webinar has been recorded. It will be posted later on the RepartTrade platform, as well as distributed through our different channels. We will be back next Wednesday for episode 330, and we're going to be talking fire extinguisher and driver safety. So thank you very much for being with us today. Let's go racing, and we'll talk next week. Bye-bye.
Thanks, everybody.
All right. Thank you.
RepartTrade is a digital platform that we've created basically to make life easier in the business community of auto racing.
RepartTrade, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier.
When you see a product that you're interested in, All you need to do is click on request more information, and then from there it is forwarded directly to the buyer or to the supplier.
E-part trade really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
Land speed record holder George Poteet's Speed Demon rocketed 481 miles per hour at the Bonneville Salt Flats. You don't go that fast without ARP fasteners.
There is no way that we could go the speed that we've gone, the number of times we've gone, with a lesser quality bolt than ARP supplies to us. And we absolutely wouldn't be where we were today if it weren't for ARP.
When failure is not an option, it's ARP-bolts.com.
We're Performance Plus Global Logistics. Our team of dedicated performance industry and logistics experts get valuable cars and components to the track on time in top condition. We provide expedited logistics solutions for the performance industry using direct routes instead of deferred options, and communicate all necessary information to the appropriate resources to meet regulations and ensure a smooth transit and secure delivery, both domestically and internationally. And we exceed customer expectations by providing best-in-class service with an efficient and cost-effective system in place. Contact us today to book your next shipment.
You work as hard as your truck, and you have no time for downtime. That's why more truck owners trust Blue Def, America's #1 diesel exhaust fluid brand. Each batch is guaranteed pure, so you can avoid costly repairs caused by inferior DEF. Demand America's best for your truck. Blue Def and Blue Def Platinum. Put trust in your truck.
My name is Chad Sisson. I'm one of the owners of Electrified Garage. So the Shop Monkey software is great since we have the multiple locations. We can dive into each other's location and help out with appointment taking, inventory, customer communication. I can jump into Florida and help out and make an appointment down there, and vice versa. They can make appointments down there for us up here. And then by using our inventory, they can see if we have the parts, and they can get the parts ordered before the customer even comes up here.